recording, and they.
Okay.
Okay, so please.
We're still adding participants at a rapid clip, so we might want to wait. The standard MIT.
Yeah, maybe 5 minutes is too much, but 2 minutes, and then you people who miss the introduction, that's their own fault.
I think when we reach 137, like 1 over alpha, we might want to start.
There it is.
There it is. Okay, so welcome to today's seminar in a well-received series of seminars over Zoom. We have a full audience today, which is not a surprise because the speaker doesn't need an introduction. Krishna has been at MIT for, I think, a little over 2 decades now. And he's made many contributions to our field. But maybe the most important one is that he's been a thought leader for many of the time since he's been at MIT. And he has certainly been one who has helped set the tone and the agenda of our field. And my understanding is that today's talk that he's giving is assessing where we are in that overall picture, but also giving an outlook what may come next. So Krishna, it's great to have you here and to speak, and the floor is yours.
Thank you very much, Bernd, for the kind introduction, and thank you to the organizers for the invitation, but actually really much more for organizing this magnificent series over the last several years. I haven't been able to attend anywhere close to all of them, but I've really enjoyed the ones that I've attended. So to everyone, what the organizers asked me to do, my assignment from them was an introduction to heavy ion collision. And I asked, do you want an introduction to RIC beam energy scan? No. They wanted an introduction to heavy ion collisions that was much broader than that. And in fact, de-emphasized the BES part. They want me to do an introduction to the field as a whole, knowing that there have been many talks on beam energy scan physics in this series in the past and in the future. They asked me to do an introduction. So I didn't know what to do with that charge. And so I started looking at my old colloquium slides from different years past. And then I realized that we're in the middle of, or just beginning a long-range planning exercise. So I went and started looking at my colloquium slides. Why is this slide not advancing? There it is, it's just a little slow. I went and started looking at my colloquium slides from around the time of the last long-range plan, and realized that I could use the introduction from that colloquium today, almost. And that is, to me, a really pleasing sign of the robustness of the big picture that we had in 2015 or so. It also allows us to highlight where there have been very substantial developments. So I'm actually going to do that. I'm going to start with, for a good chunk of the talk, the slides that I show with minor tweaks are from around 2016. They use some slides from the long-range plan. And what we said back then remains true, that our field is responsible for a remarkable discovery, a discovery that certainly was in place by 2015, probably fine to say it was in place by 2010. By recreating droplets of the matter that filled the microseconds old universe at heavy ion collision facilities, we, meaning our field, has discovered the first liquid that ever existed. So it's fair to call it the original liquid, because if you go back earlier in the universe than the microsecond timescale, what you had was a weakly coupled plasma, not a liquid. It's the original liquid. It's the liquid from which all protons and neutrons formed. It was the hottest liquid that's ever existed, because at hotter temperatures you had a weakly coupled plasma. It's also, and this to me is more interesting than the first three bullets, it's the earliest complex form of matter. It was the first form of matter that's not a gas or a plasma, not sort of describable particle by particle that ever formed in the universe. There's a sense in which it's the most liquid, and you'll see that on coming slides. It's also, among all the different kinds of complex matter that we now know, there's a sense in which it's the closest to the fundamental degrees of freedom of the Standard Model. So this is a great discovery, and it's a discovery that our field collectively, experiment and theory, is responsible for. The processes leading up to this discovery played out over several decades. Already in 2015, the question was, what's next? All great discoveries open new challenges. So what's next for the field? That was already the question we were asking in 2015. So here goes the introduction to the field circa 2015. So what is quark gluon plasma? This new phase that I described somewhat poetically on the previous slide. Well, it's the phase of QCD that you get at high temperature. And asymptotic freedom tells us that if you really can go to T goes to infinity, it's a weakly coupled plasma of quark and gluon quasiparticles. Lattice calculations tell us that there's a crossover at a temperature of around 150 MeV, which corresponds to 20 microseconds after the Big Bang. And this is the temperature at which this QGP fell apart into hadrons. It's the temperature at which the symmetry breaking order that gave mass to hadrons developed. And heavy ion collisions are reproducing stuff several times this critical temperature. So I'm not sure why there's a delay when I click forward. Maybe if I try this. This is not good. Okay, maybe it's just, I don't understand why there's a delay. If anyone has an idea why there's a delay, because I'm using my own laptop. So here's a representative example of those lattice calculations from now 10 years ago, 12 years ago. And certainly one thing that has happened between then and now is improved lattice calculations and the calculation of many more quantities that characterize this crossover. But you can already see the message of the previous slide quite clearly in these lattice calculations. These kinds of lattice calculations, or ones from 10 years earlier, led people to a misimpression before the data came. The misimpression was that, well, if you look at the results at, say, 2TC, the energy density and entropy density are about 80% that of an ideal gas. So the misimpression, what you should not do, is to try to say whether this is a gas or a liquid based only on its static properties. You might have said, and many did, that it's a relatively weakly coupled plasma. Interactions give 20% corrections. That turned out to be wrong. It's not a weakly coupled plasma at all. The lesson that it's not a weakly coupled plasma was learned from experiment and hydrodynamics together. It could also have been learned from a large class of strongly coupled gauge theories with holographic descriptions whose plasmas have energy densities and entropy densities that are 75% of the weakly coupled gas value when the coupling is infinite. So this lesson actually could have been learned already in the late 90s, but really it wasn't. It wasn't learned until we started doing experiments. Our community started doing experiments at RIC and the LHC. And what we learned from those experiments, together with hydrodynamic calculations, of how asymmetric blobs of this stuff that are produced in the collisions, how they expand, really how they explode. These calculations compared to early data taught us that the dimensionless characterization of how much dissipation occurs as a liquid flows, namely 8/S, is much, much smaller than that of all other known liquids except one. And the except one is the next slide. So what we learned from this pre-2010, I would say, certainly pre-2015, when this slide is from, is that quarks and gluons in the quark-gluon plasma can diffuse around without being confined in hadrons. In that sense, the old picture was correct. But this QGP, it flows collectively, and its energy density and coupling are so large that the quarks and gluons are always bumping into each other. They're very far from non-interacting. it's even hard to define a mean free path because the mean free paths and relaxation times are all of order 1 over the temperature. So this thing is not a plasma in the traditional sense of what you find in a tokamak or the surface of a sun. It's much better thought of as a strongly correlated liquid. So the quarks and gluons in QGP are not confined, but they're also not free. And this discovery is really what has made QGP interesting outside of our field across a broad scientific community. So what's the other liquid that is almost as good what's the other fluid that's almost as good a liquid? It's the ultra cold fermionic atom fluid, 10 to the minus 9 Kelvin instead of 10 to the plus 12 Kelvin. The atomic physicists have tricks they can play to tune the coupling to be very strong, even though they also misname their fluid. We misname ours a quark gluon plasma. They misname theirs a unitary Fermi gas. Both the quark gluon plasma and the unitary Fermi gas are actually liquids. And in their field, they're able to take actual photographs of the expansion of an initially elliptical, actually cigar-shaped cloud of their fluid, and they see that it explodes with much greater force left to right, because the gradients are stronger in the left to right direction than in the vertical direction. By comparing quantitatively hydrodynamic calculations to these photographs, literally photographs, they're able to extract 8 over S for their fluid, and it gets down as small as around 0.4 at low temperatures. We can't do literally this. We often show pictures like this, which might give an uninformed viewer the impression that we're taking photographs of the collision in the same way that they do. But these are tracks in a detector and energy in a calorimeter, which is what this is not a photograph of the dynamics of the collision as it occurs. It's a photograph of the debris of the collision long after the explosion has occurred. But what you see is, if you look back at this, if you made a heavy ion-like photograph of this, you would see much more momentum in the equatorial direction than in the polar direction. And here, what you're seeing is the momentum of the debris, and you can see that in this particular collision, there's much more debris flowing out in this direction, much less in that. Similarly here, much less in this direction, much more in that. So you can see it with your eyes. Before I go further, there's a question about, is it legit to talk about hydrodynamics in a collision that is initially very far from equilibrium? The agreement between data about the final state and hydrodynamic calculations can be spoiled either if there's too much dissipation, that means if 8 over S is too large, or if it takes too long for the droplet to equilibrate. The already in 2015 long-standing, it goes back to Uli Heinz around the year 2000. So the already in 2015 long-standing estimate was that in order to get even a broad qualitative agreement between theory and data, the hydrodynamic description must be valid at around 1 Fermi after the collision. This was certainly in the early parts of this millennium seen as really surprising, because that seems like a very short time. That's the time it takes light to cross a proton. How on earth could this fluid equilibrate so fast? Well, who cares how long it takes light to cross a proton? That's the wrong thing to compare to. So is it really, how rapidly does equilibration occur in a strongly coupled theory? And certainly what I said in 2015 was I pointed to strongly coupled calculations like this one. This is a picture from a holographic calculation in space and time. So time on this axis, space on this axis, and you see 2 sheets of energy density colliding at this time here, and then falling apart into the strongly coupled plasma of this holographic theory. And you can analyze pictures like this and see that hydrodynamics becomes valid about 3 sheet thicknesses after the collision, roughly of order 1 over the hydrodynamic temperature after the collision, roughly 1/3 of a Fermi after a Rick collision. This was well in place in 2015. The references here you can see are from 2010 to 2013. And so by 2015, post facto, long after the early work of people like Uli, we had convinced ourselves that maybe it wasn't so shocking to have hydrodynamization occurring so rapidly. I'm going to come back to this in a minute because this is a place where there's been a lot of progress since 2015. So this is another slide which really I shouldn't show now. I'm showing it to you to highlight the improvements since 2015. So this is a 2015 slide. But I put in red now. Nota bene, this slide is from 2015. So I have today, or in 2015, given you the beginnings of a story that has played out. I then said over the past decade, now it's over the past 15 years. And if I now want to cut to the chase, what I said in 2015 was that using relativistic viscous hydrodynamics to describe the expanding cooling QGP produced not just in an initially cigar-shaped or almond-shaped blob, but in an initially lumpy heavy ion collision, because after all, nuclei are made of protons and neutrons. And using RIC data, not just on a couple of observables as in the early days, but on a whole host of observables like pion and proton and spectra and V2, V3, V4, V5, and V6 as functions of PT and impact parameter. And what I said was we could extract 8/S from the comparison between data and theory. We could get 8/S to within a factor of 2 or 3. And that's what I said in 2015. I also loved to show slides like this. This is directly from the 2015 long-range plan. This is a nice slide to make an analogy between our field and cosmology. Cosmology on the left, our field on the right. In cosmology, when you look at the microwave background radiation in the sky, you're looking at the debris of one collision called the Big Bang. And you see that the debris is lumpy. And you can quantify that lumpiness by Fourier transforming this figure and getting a plot like this. This is the Fourier coefficients that describe this. And then you have a hydrodynamic theory. There's more than hydro, but you have a theory that describes this data beautifully. What goes into this theory is initial quantum fluctuations in the cosmological case from inflation, plus hydrodynamic evolution. Okay, on our side, the analogy is not precise because these figures on the right are simulation, not data. They are a theorist's impression of what the initial state of our little bangs look like. So the comparison between left and right is actually not accurate at the top here. Because on the left I have final state data, on the right I have initial state theory. But the comparison really you should look at is on the bottom side, because on the right here I also have Fourier coefficients, but here I can plot them as a function of PT. And I have data going through them, and that data has initial state physics in it, including quantum information about the positions of the protons and neutrons in a nucleus. And it has hydrodynamic evolution, and it works pretty well. So closing this comparison, in both cases, you have initial state quantum fluctuations processed by hydrodynamics appearing in the data in a way that's quantified by Fourier coefficients. And by comparing calculations and measurements of those Fourier coefficients, you learn about the fluid and you learn about the initial fluctuations. All same for us. Cosmologists have a big advantage that they can look at L's out to, in this slide, 1,000, now several thousand. We have a huge advantage, enormous advantage, because we have billions of bangs. They have only one. And our experimental colleagues can vary control parameters because they can look at, for example, variations with impact parameter or collisions of different size nuclei. Okay. So this was 2015. What's changed? Actually, before I do that, this is the very last slide from 2015. So what's changed? One thing that's changed is the precision of the extraction of something like 8/S. I foreshadowed that. But this is the last 2015 slide. So this is where I turned from introduction to what's next in 2015. And what I said, and would still say, is that the quark gluon plasma at RIC and the LHC and the unitary Fermi gas are all, and gauge theory plasmas with holographic descriptions, are all examples of strongly coupled fluid with no apparent quasi-particles in their description. In cork gluon plasma with 8 over S down at around 0.1 or 0.2 or so, there can be no transport peak. And that means there can be no self-consistent description of this fluid in terms of quark and gluon quasiparticles alone. So a quasiparticle description is consistent only if the lifetime of the quasiparticles is much larger than 1 over the temperature. And for an 8 over S of 0.2, the lifetime is equal to 1 over the temperature. In other fields of physics, there are fluids with no quasiparticle description, and they're among the most interesting forms of matter that condensed matter physicists study today. And in all these cases, whether ours or in condensed matter, the next step after discovery, and this is what I said in 2015, I left a word out. So in the next step after discovery, I said in 2015 was probing and doping. Well, okay, that's the end of the 2015 intro, and I think it's almost an excellent introduction today. But there have been many, many, many improvements. I don't want to go through all of them, but I want to highlight 2 ways in which I think the introduction I just gave is inadequate today. One is in asking ourselves, is hydrodynamization in 1 Fermi surprising? Today, we wouldn't only point to the strongly coupled work that I showed in 2015. There's been an enormous advance in the understanding of how hydrodynamization works in a weakly coupled picture applied at intermediate coupling. This is work based on kinetic theory. It's been done by dozens of authors. I listed a small subset of the authors on the slide. I will also highlight that as of 2015, we had an intuitive and qualitative understanding of how hydrodynamization can happen so quickly at strong coupling from those ADS-CFT calculations. And I could have talked about that if I gave a seminar in 2015. But now, in addition to having a lot of, well, an enormous improvement in the formalism, a rich set of calculations, we also have intuition. And for intuition and qualitative understanding, I would point to the very new work on adiabatic hydrodynamization by these authors, which to me gives you the intuition for understanding what's going on in these calculations. So I would urge the organizers to pick from the authors of these sets of works and have someone from these groups of authors give talks in future in this series. This to me is one of the biggest ways in which my 2015 intro is inadequate today. And then the other big one is that I left out a word. When in 2015, I said, what's next? I said probing and doping the plasma. I should have said quantifying. I should have said on those slides, we can do a lot better than 8 over S between 1 over 4 pi and 3 over 4 pi at the LHC, which is what I had on the 2015 slide. We need to quantify our understanding of the characterization of this new material that we found. I could have said that as a what next in 2015. It wasn't on my slides. It should have been. Because if you look at what's happened in the last few years, there's been remarkable progress in quantification. This has come, it's impossible to list names here because it's many, many experimentalists and theorists. Together with more precise data and in many improvements in modeling, now flowing into Bayesian determinations that are being done by multiple groups and these Bayesian determinations are determining key properties of the QGP, like 8 over S, its temperature dependence, Z over S, second order transport coefficients, what their values are, plus characterizing the shape of the fluid in quite a sophisticated way, looking at the size of the subnucleonic hotspots in the initial state. So this slide, which is the 2015 slide, completely inadequate today. So here's an example of today's state of the art. I'm not going to walk through this except just to say that there are now many groups producing slides that look like this. This particular example comes from the Trajectum collaboration. 4 people, Umut Gursoy, Robert Nijs, Raymond Snellings, and Wilke van der Schee. That's the full collaboration. This particular figure comes from work by Nijs and van der Schee, which is to appear. And if I look for 8 over S, here's 8 over S, and this is a posterior after a Bayesian calculation. And you can see we're no longer saying things like 8 over S is between 0.1 and 0.3 like we did in 2015. We say here's a probability distribution for an 8 over S, which is This is the mean value of 8 over S between a temperature of TC and 2 TC. You'll have to read the paper when it comes out, but you can look and see there's zeta over S, there's second order coefficients, there's lots of characterizations of the initial state. Some things are well constrained, others like zeta over S, here's an example, which is not so well constrained. You can furthermore, in work like this, look at the correlations between what we know about different parameters. This shows you Pearson coefficients and correlation plots. Extraordinary relative to where we were in 2015. To me, one of the best ways of saying how far we've advanced is to look at not a physics slide, but an announcement of a workshop. This workshop is happening at the INT this coming January and February. These 4 organizers on the left, they believe they can run a 1-month workshop on how to use collisions of nuclei to learn about nuclear structure. If you had told any of us in 2015 that you could run a 1-month workshop on using heavy ion collisions to learn about the structure of the samarium nucleus, which is one example that they give in their prospectus for their workshop, I would have said, what dope are you smoking? The only reason that a group like this can make this proposal, get it selected for a 1-month workshop at the INT, is because of the kinds of progress and quantification of our understanding of these data that has happened in the last 5 to 7 years. So I believe this has already been discussed in this series, but if it hasn't, it should be. So this is the other, I think, big advance relative to the intro that I gave. Okay, so here ends the introduction from 2015 and then updated today in 2022. So, well, now what's next? And at the level of a slide with words like this, I would claim that the what's next question at the level of words, it's the same what's next question as we had in 2015, but I'm going to tell you about progress. So 2 kinds of what's next questions for the coming decade. What's the phase diagram of this new material? For high temperature superconductors, this is a cartoon of its phase diagram. For high temperature superconductors, the analog of the quark-gluon plasma for us, by the way, is what they call their strange metal phase. The analog of the superconducting phase for us is what we call the color superconducting phase. The analog of the pseudogap phase here is the hadronic phase for us. And we don't have a Fermi liquid phase out here on the right. Pseudogap and antiferromagnet together are the analogs of the hadronic phase for us. So exploring this has been one of the grand quests of experimental condensed matter physics since the discovery of high temperature materials. We should do the same and are doing the same. And for us, doping means not an excess of electrons over holes, but an excess of quarks over antiquarks. So I'll talk about that first. The second what next question is, how does the strongly coupled liquid emerge from an asymptotically free gauge theory? We are privileged to have a complex form of matter that is so close to the fundamental standard model Lagrangian that maybe we have a chance of understanding how it emerges. And in the last part of the talk, I'll speak about 3 different variants of this question. So exploring our phase diagram, this is a 2015 long-range plan cartoon, which has now become real. Some parts of it have become real. These experiments, Beam Energy Scan 2, this data has been taken. In 2015, this was a wish that we would take data at RIC exploring this region of the phase diagram. The data has now been taken. We don't know if there's a critical point here because those of us who are outside the STAR collaboration have not yet seen any data. The data was taken between 2019 and 2021. This data will tell us how the quark-gluon plasma changes as you dope it, because as you go to lower collision energies, you create plasma with more and more of an excess of quarks over antiquarks. I looked at my slides from 2015 for this part of the talk, and they were junk now. You can't use them, got to throw them away. There has been very, very substantial recent progress. The slides that I used in 2015 almost completely superseded. That progress on the experimental side is at this point still visible only to the people inside STAR, because the data has been taken. Those of us outside STAR are awaiting the results with great interest. On the theory side, the progress is visible to all. There's been enormous progress on theory and modeling, including by the BEST collaboration, which has provided an extensive report summarizing the work of many members of that group, but also by many others. I'm not going to summarize that here because I was asked not to, and I think that was a good, smart thing for the organizers to do, because it's been, as this work has been done, this has been described in this series over the past 2 years by many speakers. So I won't review it today. I just want to show a couple of slides. First of all, for in sort of survey mode, in introduction mode, for those who are wondering about, well, what's the advance in data? We can't show results because none of us have seen them, but we can show how many events were taken. And notice that this is number of events in millions on a log scale. Gray is before BES2. So any results that are shown publicly today come from the gray. And these are events at different collision energies shown at the top, different baryon chemical potentials shown at the bottom. Red this is not a projection. This is data in the can. This is the amount of data that STAR has taken in the BME between 2019 and 2021, or the red bars. They also did a fixed target program, which presents opportunities and challenges, which are for another day to discuss. But you can see that it extends to much larger values of mu B. Okay, so I'm not going to review, but I do want to just show the state of the data before BES2. So this is all BES1 data. And what you see here is the kurtosis, the proton number kurtosis, which is an observable, which many people have pointed out is a good observable to use to look for a possible critical point. Is there a critical point here? We have no idea. And the reason is that the error bars are as large as they are. What would you expect if there were a critical point? As you go to larger mu, so lower collision energies, this observable should drop below 1. 1 is Poisson fluctuations. It should go negative relative to 1, and then it should go positive. Above 1. By positive, I mean above 1. 1 is Poisson fluctuations. A better characterization of the baseline is actually this brown band here, which is URQMD, which includes physics that go beyond Poisson fluctuations, but have nothing to do with a critical point. And indeed, you see that there is reasonable evidence in this data that it's going below 1 or below URQMD. This green band shows the error bars expected when the BES2 data results are reported. So we look forward to this with great anticipation. But I will point out that people should not get over exuberant about this. It is possible that we may, as in this cartoon, see negative and then positive as you go from square root of S of 19 to 7. This is the optimist's cartoon. That would say that when you get to square root of S of 7.7, we should be when this data gets to have small error bars, it should be up here somewhere near, up around 2 or 3 with small error bars, well above 1 with small error bars. That would be the optimists. That would make the optimists happy. It would make everybody happy. But you can look at this data and say all these points are consistent with 1. In fact, all these points except for this one are consistent with URQMD, and this one is only about 1.5 sigma away from URQMD. So what would happen if in this cartoon the critical point, instead of being here, was way over here far to the right? What would happen is you get a bit of the pink lobe, but before you got into the blue, your freeze out would be occurring far too low in temperature for you to even see anything to do with the QCD crossover. So if the critical point is far off to the right, what you should expect is a little hint of negativity and then not much else. And that might be what we get. And that would be a non-discovery. That would not be a discovery with a critical point. It would be a hint that there might be a critical point at much higher chemical potentials. Unfortunately, it would mean that it'd be very hard to discover that critical point experimentally, because at those higher chemical potentials, heavy ion collisions don't get anywhere near to a possible critical point. So I'm just saying that this data can be looked at optimistically or pessimistically. We need to find out what actually happens when the measurements are made. Okay, that's all I'm going to say about doping the quark gluon plasma. Could say much more, but that's been the topic of the RIC BES seminar series on many other Tuesday mornings. So the second one, and the message is, ask other speakers to summarize the state of theory. It's the enormous advances, and we wait with great anticipation to see the new data from RIC BES2. Let's see what happens to these points once they have error bars that are as small as this green bar. Okay, last part of the talk, doing okay actually. Last part of the talk, I might go about 5 minutes over. Last part of the talk is a question that we are privileged to have a chance to address after our discovery of our new form of complex matter. And it is the one I posed once before. How does the strongly coupled liquid emerge from an asymptotically free gauge theory? So 3 variants of this question. What do I mean? So it's the word emerge is a beautifully fuzzy English language word. And it's used in different ways in physics also. So the way I wrote it here, how does the strongly coupled liquid emerge from an asymptotically free gauge theory? Emerge as a function of what? Could be emerge as a function of resolution scale, emerge as a function of time, or emerge as a function of droplet size. So I'm going to spend the most time actually on the first form here, but let me highlight all 3. So one meaning of emerge is the sense of the word that's used in condensed matter physics. Emergent structure as you coarsen, if you start with the fundamental laws at a microscopic scale and then coarsen your microscope, look at longer wavelengths, what new structure emerges. So with that sense of the emerge, if we want to see how our liquid emerges from asymptotically free QCD, with that sense of the word emerge, we need a microscope to look at smaller and smaller length scales to see the length scales over which this, as a function of length scale, over which you have the transition between asymptotically free quarks and gluons to strongly coupled fluid. So how does a liquid emerge when you coarsen your resolution length scale to look at this fluid with a resolution that's of order or smaller than 1 over the temperature? So that's the form of the question I'm going to spend most time on. But the other 2 are great questions also. The second version is the one I already mentioned. How does it form as a function of time? That's the question of equilibration. How does it form how does it become hydrodynamic so quickly? We already mentioned that one. But these 3 questions are all related. And then the third version is, if you look at what's the smallest droplet, if you go to smaller and smaller and smaller droplets, at some point you can't talk about a liquid anymore. What is the smallest droplet? So how does this liquid emerge as a function of increasing system size? Answering each of these questions, each of these 3 versions of the same question, tells us in a different way about how the QGP responds to being stressed or probed, and tells us in a different way about its inner workings. So all 3 of these are great questions for our future. I have spoken already about great progress in theory about bullet 2 here. I want to do 1 slide on bullet 3, and then we're mostly going to talk about bullet 1, although you will see that bullet 2 creeps into bullet 1. So bullet 3, small systems. We theorists missed the boat here. Long before P-led data was analyzed at the LHC, theorists had been looking at collisions in strongly coupled gauge theories using holographic methods. We didn't think to ask the what's the smallest droplet of fluid question, but we could have done it before the P-led collisions were first done at the LHC. It just didn't occur to us. So this question of what's the smallest possible drop of liquid was actually posed first by experimentalists looking at P-led data from the LHC, and soon thereafter P-gold, D-gold, and helium-3 gold data from RIC. And seeing things that looked liquid-like in data on rather small collision systems. Another thing that was happening at around the same time was people were looking at using hydrodynamics to describe the evolution of initial states with small lumps in it. these small hotspots, subnucleonic hotspots, their evolution was being described hydrodynamically, and it was agreeing with data. That's another sign that hydrodynamics is working on quite small systems, in this case, small lumps within a bigger droplet. Okay, then the holographic calculations came after that. This question was first asked from experiment, and subsequent holographic calculations showed that you could get hydrodynamics as a good description of the final state as long as the collision was big enough that its size times its hydrodynamization temperature was bigger than about 0.5 to 1. And post facto, post hoc, this suggests that maybe it's not surprising that in P gold or P lead collisions, you could describe the final state hydrodynamically. This was a post facto conclusion. Here again, there have been many, many recent theoretical advances using kinetic theory and looking at how hydrodynamics and kinetic theory are related. And again, a posteriori, this result that we see fluid-like behavior in small collisions has started to feel less remarkable, but really it's still in fact remarkable. So this will not be our focus for the remaining 20 minutes of the talk, but it is important for the remaining 20 minutes of the talk because it tells us that if we want to see inside the liquid, to see its microscopic degrees of freedom, to see the asymptotically free, to see the emergence as a function of length scale, to get closer to the asymptotically free gauge theory, we have to resolve the fluid at very short length scales, because already on length scales that are 1 Fermi or even half a Fermi, it's behaving like a fluid. So we need probes which will resolve length scales that are short compared to, let's say, half a Fermi. And this tells us that this is going to be a challenge. The only chance we have of rising to this challenge comes from looking at jets and heavy ion collisions. And the reason why this is interesting is, to me, the long-term motivation of looking at jets and heavy ion collisions is what I just said. The remarkable utility of hydrodynamics tells us that if we want to see how this liquid is put together from quarks and gluons, we need probes with much finer resolution than 1 over the temperature. That means much finer resolution than the size of a proton, much finer resolution than the size of the lumps in the initial state that behave hydrodynamically, much finer resolution than 1 over the hydrodynamization temperature. All of those are scales of around half a Fermi. So we need resolution scales much finer than half a Fermi. And the only one I know in our business are jets. But jets are not simple. They are multi-scale probes. They're not literally a microscope where you can dial the setting. They probe the plasma on many scales all at once. The scales associated with the physics of jets and heavy ion collisions range from very hard to very soft. The production of the hard parton that becomes a jet is a very hard process, but the response of the medium to the jet is soft physics, and there's everything in between. So in my opinion, jets provide our best and in fact only chance of seeing the inner workings of the QGP. They're the closest we're ever going to come to doing a scattering experiment off a droplet of Big Bang matter. Look and see hard partons in a jet. How do they scatter off of things in the plasma? But there are a lot more than that, though, because actually jets are also give us the best chance of watching how quark-gluon plasma relaxes, equilibrates, hydrodynamizes. And the reason for that is that a jet in the plasma, in addition to looking at how a parton scatters off the plasma, you have to look at how the plasma responds to the jet, because all of that is, when an experimentalist measures a jet, part of what they're seeing is the response of the plasma. And the wakes that the jet leaves in the fluid are initially out of equilibrium, but then they hydrodynamize, and that happens much later than the initial formation of the fluid. So the best experimental shot at having access to the physics of hydrodynamization actually comes from jets also. So jets are wonderful, but they're very complicated. And it's precisely because they're multi-scale probes that they're not easy. It's not easy to decode what they're trying to tell us, because they're telling us all at the same time in the same jet about the nature of the QGP at many length scales. The modification of jets encodes information about the wake in the plasma at scales, which is at long scales, hydrodynamic scales. It also encodes information about hard scattering. It encodes information about radiation. It encodes information about all kinds of physics. So how do we separate effects on experimental observables, for example, coming from the wake in the plasma, from those coming from partons in the jet scattering off of hypothetically, partons in the jet scattering off of quasiparticles in the fluid? This is the challenge that I'm going to speak about in the last 15 minutes of the talk. So when looked at with sufficient resolution, quark gluon plasma has to be made of weakly coupled quarks and gluons. Gross, Wilczek, and Pollitzer can keep their prize. QCD is asymptotically free. And so in order to begin asking the question of how does this strongly coupled liquid emerge from the asymptotically free gauge theory, we need experimental evidence for the point-like scatterers in the QGP. To see that, we need to probe the QGP with large momentum transfer. For that, we need jets. We need high statistics jet measurements, which is not easy, but that's the challenge ahead of us. This is why a large community of experimental physicists are building Phoenix, which will start taking data in February. And this, to me, is a big motivation, although not the only one, for the high luminosity LHC program, which is about to start also. It's also why theorists, a large community of theorists today, are doing an enormous amount of work to build the baseline of understanding against which to look for such effects. Okay, here ends the introductory. That was the introduction. That was the sort of the survey version of looking ahead. The last 15 minutes will be a 15-minute seminar, not colloquium style, not introduction. The last 15 minutes is a sort of conference talk report of recent work by Zach Hulcher, who's a grad student in experimental neutrino physics at Stanford, who continues to work with me and Danny Pablos. He was an undergrad at MIT, which is how I started working with him. So he's an experimental neutrino physicist doing strongly coupled theory work at the same time. Danny Pablos is a very accomplished postdoc in our field. I expect that many of you know him. This reports on work that we showed at Quark Matter. The first archive number is the Quark Matter proceedings. The paper with the full exposition is coming soon. And we wanted to do a study to look at which observables are good observables to use to look for effects that are sensitive to the presence of quasiparticles in the QGP. And the motivation for this I've given you in the first 45 minutes of today's talk. This talk, this 15-minute seminar at the end of a 1-hour talk, is also a good example of a lesson of what you can do with a model. There are things you can do with a model that you can't do with experimental data. The model I'm going to use is called the hybrid model. I'll show it on the next slide. You can turn physical effects off and on in a model in ways that you cannot do in experimental data. And this provides us with not quantitative comparisons to data, but ways of identifying which observables are more sensitive to which kinds of physics. And that's what I'm after here, not quantitative comparison to data, but asking which observables are more sensitive to the presence of quasiparticles in the soup, in the strongly coupled fluid, and which ones are more sensitive to the wakes that the jets make in the soup. So first, a one-slide intro to the hybrid model, which is the model I will use. The hybrid model is a model for describing jets and heavy ion collisions that is like one of those figures in Greek mythology with the body of one animal and the head of a different one. It's built by starting with a parton shower that you take from Pythia, which is built upon perturbative QCD, DGLAP evolution. So we take parton showers from Pythia, and then we embed them in. Here's a parton shower from Pythia shown in red. We embed it in a blob of QGP, which we describe hydrodynamically. And we then say every parton in the shower loses energy. These red backward arrows are a cartoon way of saying they're feeling friction, they're losing energy. And how much energy they lose Well, to describe how much energy each of these partons lose, we take a result from a holographic calculation for how much energy partons in a strongly coupled fluid lose as they plow through that fluid. The strongly coupled result, so this is the holographic where holography enters. This strongly coupled result has one parameter. That parameter is known in n=4 supersymmetric Yang-Mills theory. That's not our world. So we treat this parameter as an order 1 fit constant. More about that in a minute. Well, these partons are all losing energy to the fluid. That energy has to go somewhere, and it forms a wake in the fluid. So if there are ripples in the fluid, that the lost energy becomes ripples in the fluid. Those ripples in the fluid turn into particles, turn into hadrons in the final state. And in 2016, we gave a very crude description of the final state particles from the wake, and that's what we're using in the results I'm going to show. I will say another work in progress, which I'm not going to talk about today, is developing much better treatments of this wake. This is something which Xiaojun Yao and Danny Pablos and collaborators are working on and could talk about. That paper is coming soon also. And I'm one of the et als in that too. So we're going to add this is the model described in the literature previously. We're going to add to it. We're going to add Molière scattering. Why? Why are we doing this? Well, in the hybrid model to date, there are no quasi-particles. The hybrid model to date has energy loss. It has Q hat. It has a Gaussian distribution of transverse momentum that every parton picks up. It describes a wealth of data reasonably well, but not everything. And it has no quasi-particles. So it's actually a very good way of getting a sense of what you can describe about the physics of jets and heavy ion collisions with no particles in the fluid. And that's how it's been used up to now. But we know there are particles in the fluid because QCD is asymptotically free. So once in a while, high energy partons in the jet have the potential to see those particles by scattering off of them. That's called Molière scattering. And seeing such Molière scattering is the first step to probing the microscopic structure. That was the introduction to the talk today. And if you want to ask the question, which jet observables are sensitive to this effect, you have to be able to turn it off and on. And the hybrid model is really, really good at turning it off and on, because when this physics is off in the hybrid model, it is really off. There are no particles at all. In the hybrid model, without the addition I'm about to describe, there's no particulate physics whatsoever. So that makes it a very good baseline in which to look for the effects of quasi-particles if you figure out a way of adding them into the model. So the work of Hulcher, Pablos, and myself, this is the summary of the rest of the seminar. We want to add Molière and look at its effects. Both are challenging. So here's how we add Molière. We build this on work that I did with Francesco D'Aramo and our host, Yi Yin, a few years ago. A few years ago, these authors looked at Molière scattering off a brick of quark-gluon plasma. Here's an incoming parton. It scatters off a medium parton. You get two partons coming in, one from the jet, one from the medium, two partons going out at angles and energies, which we learned how to compute. What we now want to do is we want to take this calculation and use it to change the hybrid model. Before we do that, though, a couple of remarks. One is, so these are results from the brick calculation. One thing which Zach has done is to take the brick calculation from 2018 and do everything, almost everything analytically in a way that will make it much easier to implement in a jet Monte Carlo like the hybrid model. But before I do that, you have to look at kinematic plots like this. This is still for a brick. This is from one of the outgoing particles, its momentum on the vertical axis and its scattering angle on the horizontal axis. And there's a region here that you have to exclude because this is the region of low momentum transfer. And you shouldn't use a tree level calculation just to describe low momentum transfer physics. You should only use it at high momentum transfer. So one of the things we're doing is excluding the region to the left, to below and to the left of this green curve here. We have to do something similar to exclude small u. That's not a simple curve on this plot, but we have to do that also. We have analytical results, which are then fast to sample in a Monte Carlo. And then what we have to do is in the hybrid model, for every step dt in time, here I have 1 parton in the shower, here I have 2, here I have 3, here I have 4. Every step dt, every parton in the shower, treat the plasma as a little brick with thickness dt and ask what's the probability of scattering. So we use brick results to ask dt by dt by dt, what's the probability of molar scattering? And once in a while, a scattering event will occur. Here in the cartoon, it happened twice. So if you look at the cartoon, this was the jet as reconstructed without molar scattering. In the cartoon, there were 2 scattering events, and now the jet has 3 prongs. That's the idea of what we're looking for. But we now have a way of implementing this in the hybrid model. It's, by the way, it's incredibly rare that would happen twice in one event, but for the cartoon, there you go. And after each such scattering, the subsequent partons then each lose energy. They each make a wake. So, and then we can do look at results. Though before we look at results, one last slide before results. The elastic scatterings can also, soft elastic scatterings result in Gaussian broadening. This is the physics of Q hat, but and this is an extraction of Q hat from data by the JET collaboration. But Q hat arises without quasiparticles in a strongly coupled fluid, and adding Gaussian broadening without quasiparticles was done a number of years ago and actually has very little effect on jet observables. One of the reasons why we restrict in this calculation to momentum exchanges that are large is to avoid double counting this soft physics, which we already know about. Okay, getting to results. So before we get to results, you have to refit the 1 parameter. That is the 1 parameter of the model. We refit that by making sure RAA doesn't change. This is for the aficionados. Let's go to results. Okay, the first thing you might look at, so scattering should broaden jets, right? So let's look at the jet shape and just look for broadening. It should increase the number of particles in the jets. Let's look at the fragmentation function. Those are sort of gross observables that are the first things you think of. And for every one of the next slides, there's going to be a gray curve, green curve, blue curve, red curve. So let me orient you here as to what's what for the 4 colors. So gray is results from the hybrid model with no molar scattering and no wake in the fluid. If you start from gray and add a wake in the fluid, that takes you from gray to blue. Blue is no molar scattering, but include the effects of the wake on the observable you're looking at. Then you add molar, that takes you from blue to red. Or you can start with neither, add molar scattering, that takes you to green, and then add the wake, that takes you to red. So anytime you get a result like this, you go, oh, this is a good observable for looking at wakes. Because look at this, to see the effect of the wake, I can look at red versus green. They're well separated. There's a big effect of the wake in this observable. What about molar scattering? That's red versus blue. Much smaller effect. So molar scattering does affect the shape of the jet. It does affect the fragmentation function, but it does so in a way that is similar to what the wake does and much smaller in magnitude. So these are observables that will show effects both of the physical phenomena we're looking at, which here we can turn off and on in a clean way that no experimentalist will ever be able to do. And yes, there is in principle sensitivity to molar, but in practice, these are useless if you want to study molar scattering. Look for the effects of scattering, look for quasiparticles, because the wake is much more significant. So this suggests looking at groomed observables. The next 4 slides are groomed, few slides are groomed observables. This is the groomed ZG and RG. I won't define terms here, but these are groomed observables, and grooming strips away soft particles in a controlled way. And look, it works. Here, red is close to green. That means the effect of the wake is small. So you've gotten rid of the effect of the wake. This is a much better observable for looking for effects of molar scattering, because the molar scattering effects, red minus blue, are bigger than the wake effects, red minus green. This is another example of a groomed observable, same conclusion. So molar scattering effects now show up, and they're larger than the wake effect. So these groomed observables are a better choice if you want to look for molar scattering. But the best choice that we found are observables that directly look for this, what I showed in the cartoon. So the effect of Molière scattering, the wake pumps lots of soft particles into the final jet, but it doesn't make the jet more prongy. Whereas Molière scattering makes the jet more prongy. So the best observables to use to look for Molière scattering are those that look for example, jets within jets. So you reconstruct R equals 0.6 jets, you look at the particles in R equals 0.6 jets and look inside them for R equals 0.15 jets. So you look for jets inside jets. And you ask, how many subjets inside a jet do we find? And the number of subjets you find goes up. You ask, how are the subjets distributed? And you find that they are more widely separated from each other, and they're farther away from the center of the jet axis when you include Molière scattering. This is our suggestion as to the cleanest observable to use to look for the physics of scattering off of quasiparticles in the plasma. Because the physics of the wake doesn't do this. Okay, I'm going to skip the next bunch of slides and go to the last conclusion slide because of the time. For this is, I don't know whether we have colleagues of experimental physicists who are looking for this physics using ecoplanarity. We looked at a bunch of ecoplanarity observables because many experimentalists have been measuring them, and also because 10 years ago Francesco D'Aramo and Hong Lu and I suggested these as good observables to use to look for quasiparticles. Turns out we were wrong. They turn out to be more sensitive to the wake than to the presence of quasiparticles, because the effect of the wake is the wake doesn't kick a jet, but the wake means that when you reconstruct the axis of a jet, you're off. And the inaccuracy in the reconstruction of the jet axis caused by the presence of the wake results in bigger ecoplanarity than Molière scattering does. That's the message of a bunch of slides. We looked at Z-jet ecoplanarity. I'm going to skip these. We looked at hadron charge jet ecoplanarity at RIC and hadron charge jet ecoplanarity at the LHC. If there are experimentalists who measure these observables in this audience, we can go back to these slides. But I want to conclude with this last slide. So in the seminar part of the talk, we looked at the effects of power law rare large angle scattering, Molière scattering, on jet observables in the perturbative regime. Molière scattering affects many observables. But for the overall shape observables, like jet shapes and fragmentation functions, the effects are small and similar to they're smaller than the effects of the wake and similar to them, so forget it. You won't discern them even though they're there, because they're swamped by a bigger physical phenomenon. Grooming helps because it removes the soft particles from the wake, or most of the soft particles from the wake. So the effects of Molière scattering can dominate the modification of some groomed observables. The best kind of observable that we found are jets within jets, so subjet observables. These are unaffected by the wake because the wake doesn't make a jet have more prongs. And they reflect, therefore, what's interesting is they reflect that aspect that makes the effect of scattering different from the effect of the wake. Let me highlight here, I've described a model study. Model studies have weaknesses as well as strengths. These subjet observables can be affected in other ways too. Molière scattering is not the only way of having medium-induced modification of subjet observables. But this is actually great. It's not a problem. It's a reason why our model is incomplete, but it's not a problem. The point is that you don't, in the strongly coupled fluid, a jet does not sprout prongs. And so whatever other physics there is beyond Molière scattering that results in modification of subjet observables, it's also coming from the particulate aspects of the QGP. So even if we don't have the whole story, which we certainly don't, I think the suggestion of looking at these observables as ways of seeing the effects of the particles is sound. And ecoplanarity observables, unfortunately, are more sensitive to the physics of the wake. That's the part that I skipped. And the future, in the small sense of future here, is studying charm observables. I could explain that these last two bullets are related, and I didn't really have time to talk about that. So this is the conclusion of the seminar. The conclusion of the introduction was 20 minutes ago. And so Bernd, I will stop now and take questions, and I have not been reading the chat.
Thank you very much, Krishna, for this fantastic overview and review, and also forward look. I'm sure there will be many questions. For the moment, let me come back to what happened in the chat in between, because you missed that. And there was a question by Jean-François Paquet. And Jean-François said, is there a tension between the previous slide, which highlighted the impossibility of describing strongly coupled QGP with quasi-particles? So this refers to the 2015 part.
Yeah.
And the top that points out a new understanding of hydrodynamization coming from kinetic theory. In other words, is there a tension between the two? Because maybe now we can distinguish.
Well, I don't know whether tension is the right word. I think that now we have two viable ways of describing hydrodynamization. One is to say, let's try to describe, and neither can be correct. So one, the strongly coupled way is to say, let me describe the initial state as if it were strongly coupled from time zero. Certainly not correct, but seems to describe very rapid thermalization, or very rapid hydrodynamization. And some of the, by the way, some of the Bayesian studies are using that as a way of describing the initial conditions. Some of them, but others of them are using kinetic theory. The kinetic theory description also can't be correct, because you can't use kinetic theory all the way to, you can't use kinetic theory forever, or if you use it forever, then really what you're doing is hydrodynamics. And so in the kinetic theory description, you're taking a weakly coupled picture and applying it at intermediate coupling, which I said. So neither of them can be correct, but both of them are correct and neither of them is correct. And so I don't know whether I would say there's a tension. I would say there's an opportunity, which is we have, as so often happens in QCD, we have physics which always lives in the middle. And we're describing it from one side, strongly coupled side, and trying to describe an intermediate coupling world from the strongly coupled side, or to trying to describe an intermediate coupling world with a weakly coupled picture. Both seem to be working, and hence, we leave it now to people like the trajectum folks, or there are many others who are doing Bayesian studies. In principle, it should be possible to use Bayesian methods to constrain our to start to say which of these approaches works better. I don't know whether we're close to that quite yet, although others may want to comment.
But it also suggests that a more complete theory that has these two limits would be of interest.
Yeah, and if I still have my slides up, right? You can still see my slides?
Yes.
Okay, so if I go way back, and I will just, for fun, go back to the trajectum slide, and look for, yes, this one here, this parameter RHYD. It's the second to last little panel of all these panels. This is in the unpublished work. It's the work that is to appear soon, but I got it from Robert this weekend. This parameter it's a model parameter. It's not a theory parameter, it's a model parameter. But 0 means kinetic theory and 1 means ADS-CFT. So they basically, in their model, they have two ways of doing the initial state, the kinetic theory way or the ADS-CFT way, and they have one parameter that they can dial that takes you from one to the other. 0 is kinetic theory, 1 is ADS-CFT, and the posterior probability distribution favors 1. So wait for the paper to come out, and then everybody should shoot at this, okay? If you take this as the final word, which you should not, but if you take this as the final word, it says that the data favors a strongly coupled initial state. Now, you have to look and see, how did they do this? How did they put in a one parameter that varies from one to the other? Other people will try this also. This is not the final word, but I think it's the state of things to come, but it's not the final word.
Okay, let's now turn to the hands raised. Claudia Ratti is next.
Yes. Hi, Krishna. Thanks for the very nice talk.
Hi, Claudia.
I would like to ask about when you showed the star data and you said potentially for the net proton kurtosis, you said potentially the data could be still all consistent with one, and then would mean that if there is a critical point, would sit high in the high density or highly doped, to use your
Yes.
word, phase of matter. So in that case, what would be, in your opinion, our best shot at still trying to find it in the future somehow?
Okay, so let me first of all restate what I said. I don't think this energy here, this is 29 GeV or 27 GeV. This is a clear deviation, a statistically significant deviation below 1. This one is more than 2 sigma below 1. It's about 3 sigma below 1. If you take these two together, there's with these 2 points together, there's a 5 sigma deviation below 1 for sure. That's not going away. I mean, these error bars will get smaller, but that's not going away. What I was saying was these 3 points on the left.
Right.
Okay. These 3 points on the left at the moment are all consistent with 1. So first of all, I just wanted to clarify that. So suppose these 3 points, the pessimist view is to say, well, suppose these 3 points, let's say they all ended up right consistent with URQMD. Suppose they end up with small error bars right on top of URQMD. That's the pessimistic possibility, unless you are an author of URQMD, when of course it would make you happy. And in that case, what would we have seen? We would have seen some small hint of negative and then not much else. To me, what that's a sign of is we started to get the very beginnings of approaching, we're still far away from it, but we started to see some hint of, but then freeze out dropped to lower temperatures, the freeze out temperature fell away from the critical curve, and we're not freezing out at high enough temperatures to see effects anymore.
Right.
So unfortunately, so look, you're having pessimistic Krishna here, okay? Pessimistic Krishna, if that's what we get, then going to do heavy ion collisions at higher mu-B, lower collision energy, for example, through the star fixed target program or at CBM at FAIR, doesn't help because it goes to even lower temperatures. It doesn't help. So what we need is a breakthrough from lattice theorists like you. Okay, our best hope is the lattice, but it requires a major breakthrough, and this is pessimistic Krishna. So let's hope pessimistic Krishna is wrong. But it's important to basically to bracket. In reality, I'm somewhere between pessimistic Krishna and optimistic Krishna. The optimist would say, "Oh wow, look at this! Look how high this looks. Error bar, schmerror bars. Ignore the error bars. Look where the central point is. Let's assume it stays at the central point." Right? You should never do that as a theorist. You always should take error bar seriously. But if you make that mistake, suppose that at square root of S of 7.7, we end up with a small error bar result up here. That's a huge discovery, because then we have clear negative here, clear positive there. That's optimistic Krishna. In that case, it's very interesting to go down here and get more points. It's very interesting to get more points because this, I didn't highlight it, but this is at root S of 3 GeV. This is URQMD. This is star. This is hot S. So down here, we're clearly at root S of 3 GeV. We are no longer exploring the crossover region. We're in the hadronic phase. It's URQMD, folks. This is URQMD. So if the data were to be, if optimistic Krishna, if we get lucky, if optimistic Krishna, we get a data point here, then you want to see how this turns off. How do you get from there to there? That's when star fixed target, if they can do it, CBM, if FAIR gets built, that's when it gets interesting. But for right now, with the error bars here, you can't rule out the pessimistic possibility.
Yeah.
And in the pessimistic case, there's no reason to go look at lower energies. So anyway, you can all, it's up to taste whether you're optimist or pessimist, but the data don't dictate optimism or pessimism.
Thanks.
Uli.
The next question was by Ulrich.
Yeah, I wanted to come back to the question of Jean-Francois and the response by Krishna. So I think what's known is that you can reach hydrodynamic behavior in strongly coupled systems and in weakly coupled systems very quickly, but for completely different reasons. And that evidence stems from investigations that all share one feature which is a high degree of symmetry, because they are almost all of them in pure cane flow. So to what extent this is robust in general three-dimensional flow is still not completely known. It may not be crucial, because if it holds, pure cane holds for the early, we all think that pure cane holds for the early stage of the collision. And if all the interesting stuff happens already during that very early stage, then that this is not universal when the system turns three-dimensional may not be a big issue. But this is all something that is still needs to be worked out. What I would say is that from the fact that systems behave hydrodynamically, you cannot go and draw conclusions about the particulate or non-particulate structure of the medium that is underlying.
Exactly. So I think I agree with 7/8 of what Uli just said, if I'm counting correctly. What the thing he said at the end is by far is really important to understand. The hydrodynamic picture does not tell you hydrodynamic picture doesn't tell you anything about the particulate or nature or lack thereof. Hydrodynamic picture applies to strongly coupled fluids in an ADS CFT description, which are fluids at all length scales, which is not QCD, but hydrodynamics works beautifully. Hydrodynamics also describes kinetic theory at late times and long distances. That was the last thing. The one thing I will, in terms of the earlier things you said, Uli, the kinetic theory calculations are, I believe, I agree with you that they're all done with assuming Bjorkane, not for the strongly coupled ones. The strongly coupled collisions of sheets do not assume Bjorkane. They have, but they have a different flaw. They have far too much stopping. If you look at the rapidity dependence, the physics as a function of rapidity, it is very, very non-Bjorkane, but it has far too much stopping. Anyway, that's a detail on top of what you said.
I give you that 1/8. Fine. Yes.
That's the 1/8.
So while other people think about whether they want to raise their hand, which I would strongly encourage, Krishna, let me ask you a question concerning the last part of their talk. You pointed out that really one of the most interesting features of jets in the medium is the pronginess. And you pointed out that quasi-particle scattering contributes to that and might be a good way of producing it if it is observed. I wonder whether the radiation, the secondary radiation in the medium, which is the normal radiative jet quenching, can produce a similar effect, or whether they are clearly distinguishable.
Yes. Okay. So that's what I was alluding to with this bullet on the last slide. Subjet observables may also be influenced in other ways. So radiation is what I was thinking of. In the hybrid model, energy loss occurs via friction, if you like, not via radiation. So to really do a complete study and to make plots for these subjet observables that you would say this is reliable theory and should be compared to data, you'd have to include both radiation and Molière scattering, which we have not done. The thing to say, and there is one model which includes both, and it's Joule. Okay, in Joule there is radiation, in Joule there is also Molière scattering. The issue with Joule is it's very hard to turn those off in a clean way, because if you turn those off, you've turned off energy loss. It's not clear to me in Joule exactly how to do a study that would be the analog of what we just did. But it's also clear to me that what we just did by leaving out radiation, which you can think of it as either a bug or a feature of the hybrid model, that energy loss does not occur via radiation. There is no radiation in the hybrid model. It's a bug or a feature, but it's a fact. And so that's in fact exactly what I was thinking about with this bullet on this slide.
Okay, thank you. Nushu has raised his hand.
Yeah, hi, Krishna. Thank you for this.
But by the way, Nu, before you ask your question, that's a very common Zoom background for you. I've seen you use this background many times. It makes you look like Ernie Moniz. Because that tree looks like your hair.
I see.
That tree looks like your hair, and that the only person I know with hair like that is Ernie Moniz.
That's true. This is the oak tree on the path I hike every week.
Ah, wonderful.
You mentioned there's a workshop in next January about basically, if I understand, it's a nuclear structure using high energy heavy ion collisions to study. My question is, from that program, I assume it's happening. Do we want to learn about nuclear structure, or do we want to learn we want to learn its initial conditions? So, which I'm a little bit,
Well, so I don't know whether any of the proposers are in the audience. If any of the people who proposed that workshop are here, they should raise their hand. I am not a proposer, and I'm not even planning to attend. So I find it striking. So I'll tell you what I think their motivation is. But if they're here, please raise a hand and you can say your motivation. But what I think the motivation is, a lot of it starts with the isobar run. And in the isobar run, Rick did zirconium, and ruthenium collisions with the same different charge, but also different shape. Zirconium and ruthenium isobars have different shapes. The STAR collaboration has now shown data in many conferences in which they argue that they can point to specific attributes of the final state data, the correlations among VMs, and say this is how we can see the effects of the prolateness or oblateness. I actually forget which it is, but the shape of ruthenium versus the shape of zirconium. And so this workshop is keyed off of that, and to say, let's do more physics like that. So there's, in the proposal for the workshop, they use samarium and I think mercury. They pick several nuclei that could be collided, and I've forgotten. I know samarium is one of them because it's such an unusual nucleus. I mean, who's ever heard of samarium before? They propose samarium as one, and the idea, I think, is both. I think the idea is to say, well, look, we can actually constrain the oblateness or prolateness or quadrupole moment of samarium nuclei using heavy ion collisions. They want to claim that will teach us something about nuclear structure, which is not currently well known. But the other thing that they will be doing is further benchmarking the precision of our understanding of initial state effects on final state observables in heavy ion collision physics. So I think it's both. Uli raised his hand. Uli, are you one of the proposers?
I've been in deep discussions with one of the proposers or several of the proposers.
Yeah, and by the way, just to say, to me, the reason I showed that slide is not to say everybody go to the workshop, because will it be a good workshop? I don't know. But to say, it's inconceivable that in 2015, anyone could have proposed such a workshop. If you would put that proposal into the INT in 2015, the decision-making body would have laughed you out of town. You are nuts that you think you can do that. And it's the fact that our field has gotten so much more advanced in the direction of quantification and uncertainties and correlation between uncertainties and Bayesian approaches. It's that fact that has meant that this proposal was proposable and was acceptable to the INT and is happening. And kudos to the whole field for getting us to this point. I've never spoken with the organizers about their proposal, but that's what I was trying to say. Uli, if you've actually spoken to the organizers, you can say more.
Well, let me just say the way you have phrased the goal of that workshop is how they see it, but I think the real goal should be slightly different. I don't think that the weakest point in this inference chain is the nuclear structure. I think the weakest point is the deposition process that deposits energy in the collision. So I think a more targeted way of formulating that program should be take the best Bayesian inference on the on the heavy ion side from the experimental data to get at the initial conditions of the fireball. Take the best nuclear structure that you can get from the nuclear structure side to get the best information on the configuration and the shape and the deformations of the nuclei before the collision. with all the uncertainties, and then use these two results to constrain the big unknown, which is how does energy get deposited in the collision in the first place. I think that is a realistic goal that should be pursued. And once that has been solved, then you can go the next step and go to collision systems where the nuclear structure is really unknown, and maybe get some information about that. But I'm afraid the errors on that will be bigger than some of the proponents think at this point.
Yeah, so that's a more sober look at what they're doing. Uli, do you think, so not the proposal, but what's been done by STAR with the zirconium and with the isobar, what do you think of the claim from STAR that they can see effects of the difference in shape from the data that they have and are looking at? You're muted. You're muted.
Yeah, I don't know. I had okay. So this temporarily unmute button works only in certain configurations. Sorry. Yeah. So I think if you buy into their hidden assumption, namely that the state just before the collision and the state just after the collision can be described by the same set of deformation parameters and the same values for these sets, then I think what they have done is very reasonable and very useful. But I question this assumption, and I think this needs to be resolved, and that's where some effort should go before we go so bold as they are to claim that they can do nuclear structure with heavy ion collisions.
So let's move on to Fujang.
Well, and wait just a second. Deborah Mrochek put something in the chat, which I can't go to right now because I'm sharing screen. But Deborah, did you want to, I don't know what you put in the chat. Did you want to say anything about it, or should we go to the next question?
Yeah, maybe I can just very quickly summarize the idea of the paper. I am not working directly on this, but I did have a discussion with Jackie just yesterday about this stuff. So basically here to just show that you can take configurations from ab initio nuclear structure simulations, and you can see effects of clustering, alpha clustering in particular, in the flow data. And this is of course all simulated, but I think it kind of goes over some of the main points of why they would propose a workshop like that.
Thank you. Okay, so let's go to the next question, Baron.
Yeah, Fujang.
Yes, hi, Krishna. Thank you very much for the wonderful talk. About the nuclear structure heavy ion collision workshop, I am one of the organizers. My name does not appear on the official list because there is a limit of 4 people and we have 6. So the idea or my motivation or my hope is that through heavy ion collisions, we can learn something about the symmetry energy. And that's, as many people said, as you said, correctly pointed out, that it was motivated by the very precision measurement of heavy of isobar collisions from STAR. And we can really, the data really confirms a prediction just from nuclear structure calculation that there is this effect of a difference in the structure can produce a difference in the multiplicity, and that's and the data really kind of confirms that prediction quite precisely, I would say. So I'm actually optimistic, much more.
So you're the optimist in this game. That's great. All I'll say is the symmetry energy, that the energy scale and the symmetry energy is tens of MeV. And so if you're able to do that with ultra-relativistic heavy ion collisions, that would prove the point I was making, which is that the level of precision of the field has advanced remarkably. So I think Uli is the sober realist, and you are the starry-eyed optimist, and we'll see what the future holds. But having a workshop, there's nothing wrong with having a workshop at the INT to hash this all out. But I'm saying that 5 years ago you wouldn't even have gotten the workshop approved. Leave apart anything further. Anyway, this was not a central point in my talk at all, but it was just I used it as a device to make the point about the improvement in quantification. I see Vilke, who is one of the Trajectum authors, has his hand raised.
Yeah, I also wanted to respond to Uli, and I'm a little bit more optimistic, of course, with Govert. We did like many of these studies using very high statistics run using isobars, and I think that there are two reasons why this will work very well. It's if you take the ratio, for instance, the effects of viscosities, they mostly cancel in this ratio. And the other reason is that you can go to very ultra-central collisions. And in that case, I mean, they're really head-on, and you really kind of see the shape in a very direct way. So I think there is two reasons why you can really see this structure.
Vilka, we lost you at the end. Or